very happy to have Andrei back. He's going to tell us about the L-genera in enumerative problems.
Thanks, man. So this is still called informal. Is that you have some word informal in the title of your seminar, or it's just no? It's just string math, or is it?
Yeah, string math.
Yeah. Okay, this will be pretty informal. So, in fact, yesterday we had this exchange with me, and I was, well, you know, like every time I'm trying to give a talk like this, I always hope that by the time the day of the talk arrives, and I'll have it all figured out, and somehow, maybe the new generations will figure it out, or maybe they already have figured out, which is I didn't understand, but. Anyhow, so this is anyhow, I was complaining to Mina that I'm really worried about the talk, and I think Mina said that the worse the better or something like that. And so I'll try my best in that regard. So so this is the setup is so maybe I recall the setup, and the setup is that this is we're doing gauge theory related theories in 2+1 special dimensions. So the space-time is it's in principle some surface that eventually will turn out to be a complex curve, and the things we want to understand sort of modulated vacuum in this theory means we have maps to some kind of x, which is so it's a modulated vacuum is will not be a holomorphic map f to some x, which is a modular space of vacuum. Like I said already, the curve itself turns out will be a complex curve, x of algebraic variety, so it will be in fact an algebraic map. And maybe another important thing to say that anywhere in physics, in particular in gauge theory, nothing takes values in a fixed. No field takes values in a fixed space. Everybody is a section of some bundle, and this is not an exception. So you should think of, in fact, there's an X bundle. There's some X bundle. We call it X twiddle. It's an X bundle over that C, and we want to count sections in some sense. And one very much motivating example, very motivating principle in this business is that we would like to have like a 3D mirror symmetry statement, and that 3D mirror symmetry statement is of the kind that there's, if I study sections like this into some X, some suitable X fibration over C, so maybe I write a schematic statement. So maybe I sum over all sections, and I have some variable Z that gives the degree, trace degree, and then it decorates by all sorts of things, and which in principle I can write any kind of. So what do we write here? We take maybe there's a contribution of the section to some virtual fundamental class or some such thing, but all these things can formally be written. So contribution to a virtual fundamental class, what's it going to be? It's going to be like symmetric algebra of some vector space, which is some cohomology, and that this cohomology you can formally write as a some kind of sum over all points of the curve. So we sort of like a product of some kind of class product of all points in C, some kind of contribution. And similarly, if we want to embed to input the data of the bundle, we can try to input the data of the bundle by saying that I have some reference bundle and I get other bundles by modifying my bundles at a point. And so this is the way you can also put it in this form. And I would like that this to be actually equal to some kind of section. These are sections going from somehow sections going to next twiddle, and then there is. So this, the way this is fixed, this bundle is maybe there's some reference bundle and then modify it at point. So there's some operator that I insert from points here. What? For count bundle is fixed, yeah. Yeah, it's fixed, yeah. So we'll get to that. And that would be some kind of mirror geometry. Next check. The dual variable. So this here the variables A, they have to do with maybe the virtual fundamental class. So there's some sort of contribution of virtual head. And then this A's enter this contribution here, and vice versa. And so, one of my delusions or dreams or something, is that formulas like this will be in particular unified with. So these formulas like this would be seen as really instances of Poisson summation formula, where you embed. So this is actual section of the vibration. This is like a global. It's a global object which you can embed into a product of all local contributions. And this would be like saying this will be analogous to the fact that if I sum over so actual sections inside the product of all possible local things, this is analogous to integers inside the reals, and then we're doing, and then this is analogous. This should be analogous to the fact that this is summation of f over n. This is a sum equal to summation of its Fourier transform. That's sweet. Okay. Yeah. So this is, but maybe more to the. More to the yeah. What? So the sum is exactly the same on both sides, right? Same thing, just exactly equal, yeah. And so it's a question. So what? So the squiggly just means we're counting sections of X vibration. Oh, so the variables A, they enter in here, through here, right? This is the variables A, they add. So A, there's some kind of group of there's some group of automorphisms of X where the variable A will live. And so when we have a way to objects like so give us a way to count things with weight, which involves variables in the dual.
What were you saying? A variables are hidden on this side.
Exactly. Yeah.
And Z variables are hidden on that side.
That's exactly right. Yeah.
Sorry, but C is the same on both sides?
C is the same, so there's always, the curve is always the same.
Is there a model example of such a thing?
Of this thing?
Yeah.
Oh yeah, this sort of thing is established in some generality, yeah.
I just want like one example of
So,
equality.
sure, so, okay, this is everybody's favorite example. Let's do, let's do this, so this is the, so where X is, so, okay, that's a good example, let's do that. So X would be T star P naught. X check is A2. What's this? This is, more precisely, this is T star of, what's P naught? P naught is A1 minus 0 mod GL1. Okay, so this is at the big, it starts, so a map, so if I have a map, I have a map to from a curve. So a map from a curve to T star P naught. Well, there's first of all the actual, maybe I'll this is what this is. So maybe let's first do T star P naught. P naught quasi map. Quasi map here is by definition is what mean map to a quotient? This means you have this. This modular space is the same as a line bundle of degree G, a line bundle L on C with a section right. So what does it mean? So when we write P naught, we say that this P naught, that's the stable locus of for GL1 action on A1. So the stable locus, if you take A1, remove 0, this is the stable locus of GL1 acting on A1, and a quasi map to a quotient. So an actual map to the quotient is an actual map to the quotient is first is a principal bundle for the group, for the gauge group, and the section of the associated line bundle, which is everywhere stable. A quasi map means it's stable at generic points. So this means this quasi map degree means a section S which is not 0. Yeah. So this is stable at generic point means it's non-zero, and then this is just SD of your curve. And so then if I take over hat on this space is some explicit K-theory stuff, K-theory class, which can in principle can be twisted according to the fact that when I start with the line bundle, I don't have to take a section of this line bundle. I can take a section of line bundle tons or some other line bundles corresponding to the fact that I can twist my T star P naught by in some way, so I can in principle do that. And so then this summation over dz to the d, well, the characteristic of this over, that really is the same as it really is the over, well, the characteristic of now going to A2, so this will be some twisting, so that will be some kind of with the space just take what am I supposed to say? I take the so this will be some twisting of this A2 over my curve will be some the space of sections, which is the sections of this line bundle. So this will be sections of the corresponding enumerative bundle. Over C, they're all virtual. And there's a way to phrase it very nicely. And then there's an example. So phrase it very nicely is rank 2. And so this has to do with so if I have so let's say I have my curve C, and I choose maybe I'll choose 4 line bundles. L1, L2, L3, and L4. So that they together, L1, L2, L3, L4, together give me the canonical class of the curve. Then the total space of this fivefold is a Calabi-Yau. So this is the total spaces. Total space. Space is 5-dimensional Calabi-Yau 5. And so then we can imagine that the C is the actual world volume of a membrane propagating in this Calabi-Yau 5. So this is a membrane. So you can, membranes, they're supposed to be 3-dimensional things propagating in 11-dimensional world. And then you can take this 11-dimensional world to be Calabi-Yau 5 cross S1. And so then you can have a Riemann surfaces cross S1 sitting in this Calabi-Yau 5 cross S1. And the general there's some general conjectures about saying that this membrane, so if I have a torus action on the Calabi-Yau 5 that fixes a threefold. So if I scale this line bundle by Z, this line bundle by Z inverse, so then the fixed locus of this preserved Calabi-Yau 5 form, this fixed locus of that is 3-dimensional. And so this is maybe call this variable Z. So this locus, the fixed locus of this little z on this is 3-dimensional. So it's L1 plus L2 over markers to 3-dimensional. And the general conjecture is that if I have a Calabi-Yau 5 thing with a fixed locus 3-dimensional, then this whatever theory of membrane is reduces to the old Downs and Thomas theory of this threefold. And so the old Johnson-Thomas theory of this threefold, what is it? It's if I have smooth, so this is my membrane, is just, it's this curve with multiplicity 1. It's not multiple, I mean multiplicity is 1. And so it's sort of kind of membranes or maybe M2 brains. M2 brains of on this Z. This is well in this case, well in general we don't have such a good theory, but in this case maybe I don't know. Maybe can consider a proof to be proven to be that's the same as DT or PT theory of this fixed locus, in which is what? Which is your curve. It's this integral. It's a summation. It's the summation of overall degree, z to the degree you take Euler characteristic of SD of C with some suitable or virtual with some twists. Twists have to do with these twists. This have to do with L3 and L4. And then, well, and then also there's a, I don't know, just write times. I'll just write times deformations. What? L3 and L4, so each of them, it's a line bundle of this threefold, and that line bundle of threefold, you can put some descendant insertions corresponding to that line bundle.
When you want PTZZ, you have PTZZ
with some descendants, yeah, with some. So, kind of deformations in L1 and L2 directions, because this curve can also move. And then the statement of the formula here says that this object here, or rather this whole thing. So maybe I'll write, so maybe brackets goes like that. And then this object here, that's just deformations in L3 and L4. So in the end, if you think about the smooth membrane in Calabi-Yau 5, well, what do you think it's going to be? It's virtual tangent space. Well, that's just going to be this just cohomology of these 4 tuples of bundles with whatever action they can have, and that would be this. This would be this answer. And then if you want any kind of, if you want to modify it, how are you going to change the twist? You can modify each of these bundles at the point, and you see, well, this has its predicted.
Why did you throw away the cogent part?
Say again?
Why did you throw away the cogent part?
Because if you want to move a curve, that only the normal bundle matters, right? If a smooth curve, its deformation theory has to do with the virtual tangents. Virtual tangent at a smooth curve are the cohomology of the normal bundle. Sorry. So that's well, let's now go back to what I was. And in principle, you should imagine, well, at least I don't know, maybe you shouldn't. But in my mind, is all the examples of this 3D mirror symmetry, it's really about it's really about trying to describe what M2 brains do in some specific background. Because instead of like, for instance, instead of taking, what you can do is you take, for instance, a finite group action on these 4-line bundles and take a quotient resolve. That would be then this would be a statement that the fact that some bundles, so if X is bundles of some kind on rank R bundles on A and surface are dual to roughly rank N bundles on AR minus R surface. That would be the state, this kind of state.
So how much of the symbolic levels can you actually engineer from this?
Well, there's just hard to say.
I mean, I'm not asking you to prove anything. Just
Yeah. Anyhow, maybe to finish with that, what I would like, well, anyhow, maybe let's move to the. Yeah, I guess, yeah. So let's move to the actual statement of the. Yeah. Cross S1. Yeah, that's right. That's right.
This is pretty much how physicists discover from these considerations.
Yeah. What I think is what sort of right. Anyhow, let's talk. The talk was supposed to be something else, about something else. So I'm happy to. Well, I don't know. Anyhow, so this is we were. So let's just recall the setup. We have some kind of X vibration. So just draw schematically some kind of X. Kind of X vibration over my curve. And I'm asking for sections. And moreover, and moreover, the way we, well, I don't know, maybe me and I, and many other people in this room, but not we as a humankind. Think about this question. They're really about. First, you can have a global curve, but first, you start with the study of things locally. You study things kind of either you want to study at a point or in a disk, or maybe in the plane with some boundary condition, or P1 with some trivialization to infinity. But anyhow, you start with things which define locally. You first start with a point, and then you imagine maybe this point is a fixed point of some kind of automorphism Q, and then you study something about maps of like I said, either formal neighborhood of this point or a disk or actual P1 with just some suitable boundary condition in infinity. You map this local object into your X, and then you want to prove some statement of this kind for this local contributions, and there's some kind of Fourier transform for this local contributions, and then maybe eventually you would be able to, if you were able to interpret the formula I wrote down on the board as some kind of analog some summation, then maybe from this local contribution, you would be able to patch some global answer. But today I want to go into a different direction and make an observation that first of all we started with objects which were a priori there were some physical objects, there was some manifolds with maybe metric or something, but then turns out in the end there were algebraic varieties, and we're doing maps of algebraic varieties. And also these local objects, they have to do maybe with, there are various ways to think about them, but in the end, whatever one sees, it's all somehow, not only the algebraic object, this algebraic object involves nothing but integers. And so it's my thinking is that you should be able to take this picture and replace it by a picture when I have some kind of x over some base c, where c is now very general. So maybe what's so good about a complex curve? Well, a complex curve, first of all, is smooth. Okay, in one dimension, so it's c is maybe one dimensional. Well, right. So now it's over. So it's now some variety x, some form of x defined over some kind of twist of x over the base scheme c. Right. So this is previously the same as x still. Yeah. So it's, this is one dimensional. Well, let's say normal. Well, maybe in the theory. but like I said, I think if you think of this story being not only the story itself, not only the question being defined essentially over somehow whatever your field of definition of Berkeley C is, but also the local thing that enters. So whatever this kind of duality interface, just some sort of just kind of object in some kind of elliptic homology of x cross x check, but that object is defined just what is the nature of C is completely, for that is just completely, seems to be completely irrelevant. So this is, so so this may be the heart of what I'm trying to say is that if I have a good enough physical understanding of mirror symmetry, that in fact produces this understanding produces an object which is maybe had some physical origin, maybe required complex numbers in the way it was set up, but in the end it produces objects which somehow involve no other numbers other than integers. And this also goes with x, right? I mean, x was a priori some kind of moduli spaces of vacuum and so on and so forth. But in the end, the things we see are like Nakajima varieties, and they're relatives, and they involve no numbers other than integers. And when I say this of course, now of course you can have instead of your gauge group, you can have some group over C. Instead of your space, you can have some space over just some height. And so what's in here? So in here, there's tons of stuff here, but in here you can take, for instance, you can take curve over finite field, or any field, but in particular finite field. Maybe this may be the most. Maybe. So what's the dimension of a general scheme? Dimension is, is what's the longest chain of closed things you can somehow closed things of different dimensions you can have. So this is one example. A curve over any field is something one-dimensional because it can have a closed point, but nothing smaller than a point. Or you can have, in fact, spec z, or spec of all or integers in a number field. There's other schemes. Let's just not talk about that. And here you can have a counting problem just like you were counting before. You can literally take and literally count sections defined over that finite field K. Literally, so you can ask about sections. You can literally take and just really count them. You can, in principle, take formal generating function of the kind summation over d, z to the d, and really the number of sections defined. Okay. This is a big issue with this problem, with this definition. This has no variable like a. And we will see some. So this is just a number. It doesn't have a. But there's a hope that this can be upgraded, which I'm not.
What was A before?
A before, so A was an element in the automorphisms of X. So that is right now has no obvious place in that formula. What? Yeah, but if you have a connecting group acting on algebraic variety, will attract trivial cohomology. So that's yeah. But this situation is not too bad, and because you can phrase it. This thing you can phrase as things like it's like the trace on the actual cohomology of the space of sections of. So this is the space of sections is the disjoint union of sections of all possible degrees. So this is in principle an infinite dimensional space, but it's graded by operator z to the d times Frobenius. Maybe you compactly support it. And that is already not too bad, because this is already, maybe I'll use, as soon as you have some sort of cohomological interpretation of what you're going to do, this is already you're a little bit in business. Because this will be, I don't know, Tony, you know how to do this kind of hide zeta function using some kind of cohomology theory?
Not sure exactly what you're referring to.
Well, we'll get to that. So this direct analog of that will not be, it's not known to me here, but maybe it exists. Direct analog, what's the analog of this, we'll discuss. What's the analog of this, that is somehow not so clear. But what I'm trying to say, if you do this, you're already not so far away from compactly supported. So this is let's just go back to the old counting. So the old counting was we took the Euler characteristic of, you take the space of sections or maybe quasi-sections. And you took z to the degree times this symmetrized virtual structure sheaf, and this contained was really dependent, involved a etc. variables in an arbitrary way. But we can, if we take this and specialize to the subgroup inside, we restrict to the subgroup inside of, so all of our x's are all symplectic, and so we specialize to the subgroup that preserves the automorphisms of x, that preserves the symplectic form. Then this is in fact, this is the business about Bern function. This is the trace, just one on H critical of this L-genera quasi-sections. So this is oh sorry, one z to the degree. So it's just the fact that if you have this kind of Calabi-Yau geometry, then you can write your if your geometry is Calabi-Yau, then you can write your modular space of quasi-section as some kind of critical locus. Yeah.
Are you explaining this in general for quasi-maps and
all of our varieties X are some sort of, there's some holomorphic symplectic reductions, so they all can be written as some kind of critical loci, and they can be put into this form. And now of course you can ask, well, it's a little far from here to there, but it's not too far because there's some kind of reductions from so what's the difference? The difference is, of course, well, maybe other than, so this is the H and dot are the same, everything in the brackets. So H dot and the brackets are the same, everything else is not the same. But it's relatable in the way that there's this kind of cohomology group there. So if I have they're relatable to that kind of cohomology group by three kinds of moves. First is so.
What is this H structure?
So let's say X is maybe Nakajima equivalent variety to be concrete. So then Nakajima equivalent variety, it's what? So maybe I'll write it like that. So this is X is maybe mu inverse of 0, some kind of mod G, which you can, so mu inverse of 0, this is the same as critical locus of a function where you pair the moment map with an element you choose an element psi in the Lie group, in the Lie algebra of G, so there's a critical locus of a function like so. And so if you have something defined as a critical locus of a function, then maps to that thing, they also define as a critical locus of something, and then they get this critical, you can define critical cohomology, But it's important that if you want some sort of group action, it's important that your group preserves this function. Since this function visibly depends on moment map, it will not be preserved by the function will not be preserved by whatever scales the symplectic form. So that you need to set things up. You need to kill the variables that don't preserve the symplectic form, and those are the variables, kind of the most important variables in the theory. And so you have to, once you kill them, it depends on no further things. Depends on just only this object. And so there's somehow, there's some kind of, one can somehow. Well, there's three kinds of moves one can use. Used to relate things like H dot crit of quasi-maps, quasi-sections to H ordinary, maybe with compact support of some kind of quasi-sections in some kind of X, to maybe ordinary sections in some kind of half of X. As follows. So, the first move is we all explain. It's just dimensional reduction. So if W is linear in some variables, maybe so W maybe summation with some coefficients bi, fi, then H crit of W is the H ordinary, sorry, H dot crit. That's H ordinary of this locus F1, F(n) equals 0. And this is the case for Nakajima varieties, because if I choose any half of the edges, that will be linear in this. And so this is just saying, if I willing to kill half of the edges, then instead of critical cohomology, I'm going to the ordinary cohomology and half sticks. Like this would be saying, if instead of T star Grassmannian, so T star Grassmannian is a Nakajima variety which corresponds to. So if I have a this kind of quiver for T star Grassmannian, and if I keep only one edge, that's the ordinary Grassmannian. Second is that right, but just as if it's linear in some set of variables, then you set the partials in these variables to 0, and then you get. So you get.
But it doesn't have to be just
This
zero
type of Grassmannian maps here, that this would be this sort of thing. Grassmannian type of thing. So then second thing is the usual thing that if I take kind of just some kind of stable locus, the homology, if I'm doing homology of some stack, that of course by restriction I can take the stable locus, but I can also, there's a way to kind of put this thing back in. This is this business about the windows and non-abelian stable envelopes and so forth. So you can write cohomology of a stack as some kind of stack. You can, generally speaking, you can write it as the pieces corresponding to various parts in the filtration. So that's one thing, and this has to do with different stabilities conditions and so forth. And the third is that if I take if I take sections, well, this is quasi-sections minus quasi-sections with actual singularities. I didn't say anything at all, right? But but if I understand cohomology of this and cohomology of that, that means the cohomology of this will fit inside the long exact sequence. And that long exact sequence, this is cohomology with the exact singularitity. This is the image. We'll talk about correspondence in a second. This is the image of the correspondences. That create singularities. And so if you'd like to find cohomology of actual sections inside this, that it means this is cohomology of quasi-sections, a module some algebra of correspondences, and you mod out by, you take, or rather the way this long exact sequences go, you take rather invariance of the subalgebra that, or derived invariance of the subalgebra that creates singularities. And so this is, so, well, I admit these things are not identical, they're relatable. And there is this, I don't know, vision or illusion or delusion or something, which says that in fact you can go back here. So if you just know this side, there is a way to reconstruct this side. And the way this goes, I mean, it was supposed to go, I mean, it goes in examples and it's supposed to go in general, is that this, you want the actual equality, then, well, geometrically it's not difficult to manufacture an actual equality as long as you put some kind of some operator. And the way this operator works is what's O virtual. O virtual, it's roughly like exterior algebra of the virtual tangent space, right? And so, but the virtual tangent space is what? If I have some kind of, if my space is a modulated space of, any kind of things like sheaves or something, then the virtual tangent space is x1 between an object and itself. And then I take exterior algebra of that space. But if I want to promote this to a trace of an operator, I can do the following thing. There's a natural way to write a bilinear expression that on the diagonal will so this O virtual is roughly, what's this O virtual roughly? It's like exterior algebra of kind of x1, or rather, it'd be even not roughly, it's like the actual exterior algebra of x1 of the full x between like an object, some kind of object and itself. Right? So on the diagonal, it's you take the Euler characteristic along the diagonal of stuff which looks like that. You want to make it a trace of an operator, you just put two things here. So you get there's an operator, that's your operator. And the question is to describe this operator in terms of, we said that this is going to be some sort of, this would be some module for some algebra of correspondences. And you'd like to describe this operator in terms of this algebra. So then if you can do it, then this would be your. And this in in reality, what this, in the examples when people can do it, this is some sort of vertex operator for this algebra. So there is this algebra has to do, this algebra has some kind of structure, and there's some notion of what would it mean to have a vertex operator for this algebra? You just stick it in here. So there's a way to, if you know, in other words, if you know the space not just as a vector space, but as a modulo over whatever algebra that's going to work on it, then you can reconstruct this thing back here. That's yeah.
As we were saying that on this side, on the left-hand side,
Yeah.
you can reformulate this trace as quadratic to really A as a trace of some operator.
That's right.
And in particular, the property is kill the A.
Yeah.
Trace diagonal.
That's right.
And so you believe that you can also write some trace also on the other side, but you don't know the names of the operators other than diagonal.
So this guy, so this is you can, so you have
Let me ask.
yeah.
So on this side,
Mm-hmm.
you have also action of the you also have a correspondence from.
Mm-hmm.
Is there something which they act on this side?
On this side, it's not clear. So this is what would that do? It's not. It's yeah. Of course, you can write a correspondence, but I'm not sure what it will do with the virtual sheaf and stuff. So that's not so clear to me. Yeah, somehow there's really good well-defined action here. That I'm not sure how to make. So this is more of a. Maybe I'll repeat. So there is of course, if you have a function of some variables and you kill part of the variables, there's no way to reconstruct the answer. But there is a hope that, in fact, if you know the algebraic structure of this space as a module over an algebra of a certain kind, which will do, this algebra has to do with this X check. I mean, not equal to it. It's, we'll explore what it has to do with this X check, and if you know enough about what this thing is as a module over this algebra, or sorry, this algebra, or some kind of sheaf on here, if you know enough about that, then you should be able to reconstruct this algebra. Okay. So
In the also in the early days of medicine,
right.
people put in Stratford, they studied distortion and showed that they weren't studying vertex functions, they were just thinking about abstract properties. It showed two things. That one, that basic statement of mirror symmetry it has the basic statement of mirror symmetry is two parts. One is that it's a Fourier transform. And two, that the most elementary example that you have written down on the board is the path integral is sort of self-mirror. So that if you apply mirror symmetry twice, just get back to that.
Okay.
That example. Do you think your thing will have like the generalization we're after will preserve those properties? If it could.
In what sense is self-mirror? You mean the
you can write this sum of a curve count.
Right.
At the end of the day, you can write it as a kind of product. But then you also observe that you would have that the left-hand side, sum of the curve count, is like a Fourier transform of that very product. So it's like a Fourier transform of the master function is that master function again. That's the basic statement of
maybe I'm.
Just
Yeah, I don't know.
Multiplying and integrating some stuff.
But
This
so.
has nothing to do with the covariant
Okay, could be. But the so
I mean, here you'll get it.
okay.
I don't know about number theory.
No, I think Spencer is probably better equipped to with the. So what's my reading of the of this hypertoric mirror symmetry? Okay, with hypertoric mirror symmetry, I agree with you that this example generates everything. And moreover, what the heart of that thing is that if I ask for what's this example? It's the so in general, that this is the this Fourier transform I was talking about. It's some. It has to be. So on one side I have a. So how am I to say it? So if you do it at kind of for the vertex function at a point that this is about this whatever duality interface or mother function for hypertoric variety, and what is it? It's just the Fourier-Mukai transform on. So this supposed to be some elliptic object, and what this elliptic object is just real Fourier-Mukai transform on elliptic curve. So there's a that's self-dual. So that's just this is that is to say. So if I have a
This is the same for it. These are the very same for it.
exactly, it's the same thing. So this is so if I look for elliptic, if I take elliptic homology of just T star T0, well, that's this is a stack, and which is a quotient. This is just elliptic curve itself, right? And then I ask for elliptic homology equivariant now, GM equivariant of this A2. That's again E. However you define these things, it's going to be that, and the objects on this too is just really Fourier-Mukai transform. There's somehow nothing. You define it. You're somehow. It doesn't matter what. You're absolutely independent of whatever was the whatever this over whatever base is this taken, or whatever base your elliptic curve lives, and you just completely independent of this. And I think it's got to be the same Fourier transform. Yeah. And my understanding is that this, in general, there's x and x check here. Then this is this elliptic class that we write on their product. That should be. That's some elliptic expression, but in particular, it should be also like its actual value should be like actual. Whatever Archimedean manifestation of this elliptic object should be also important in the actual path integral. It really integrates stuff. But in Fourier-Mukai transform, that's something that exists. Amin asked a question which I didn't understand, but I thought this might be relevant to the answer.
Well, why is it relevant to any of the rest of this?
Well, I'm just saying that the first formula, but it's not a formula, it's some kind of, it is a formula, it's interpretation of it. I was thinking that it should be really viewed as some type of Poisson summation formula where you do some sort of Fourier transform point by point, and what this Fourier transform is for the example we had at the board is just that Fourier transform is it's the Fourier-Mukai transform between these two elliptic curves.
How are you going from Fourier-Mukai transform elliptic curves to one?
What?
In the local case, when or just this local situation
Yeah.
where your curve is like 2.
Yeah.
We can like very literally interpret the Fourier transform we want.
Sorry, I mean, it's taken us a field, so maybe we'll talk about something else. So there's one. I said there is. I don't know how to put this object here over spec Z. That I don't know, but one can certainly have a count, and maybe I'll explain this by example. So this one can certainly define, and that would be and the yeah. Mm-hmm.
This kind of action algebra correspondence.
Mm-hmm. Yeah. Yeah, it depends how you proceed somehow. Yeah. I mean, my thinking about it is that if you're what?
I'm trying to ask you, which side of this equality is easier?
This equality?
Yeah, this equality.
So the hard, maybe slightly harder part is the action of this.
Yeah, right.
Yeah. But that's otherwise it's just.
Is the point of this equality that on the left-hand side, conjecturally you understand something about this kind of action algebra without thinking about this action algebra because some of it is turned into this kind of geometric parameters.
You can read it both ways. You can say that I can reconstruct this enriched function if I know the action of algebra. On the other thing, you can think of this as being some kind of enriched character theory for this algebra. And that will say, if I have a character theory which is not just takes values in, so to speak, dimensions or graded dimensions, but takes values in some parameters, then this tells me a lot more about a lot more about the algebra than otherwise. Yeah, you can read it both ways. You can say that this is. This is maybe for the reference. This kind of stuff is supposed to be called QQ characters. I'm extremely bad on this talk about any kind of reference of attributions, but maybe I should put a name and then say that this is, first studied by Nikita and
on this side.
So he was interested in something else, not in this equality at all, but he defined for the algebras that for him he was interested in assigning some kind of enriched characters for just the geometrically defined algebras acting on like incidental moduli spaces. Yeah, that sort of thing. And proving some interesting properties of this QQ character. Neither side, yeah.
But I mean, he would use it to like arrive at some instances of this thing that would like totally different.
Yeah, I think that his main thing is that this sort of this kind of theory of QQ characters, when it's fully developed, that will in particular relate things like if I have a module and it becomes suddenly reducible, then the QQ character gets a pole, this type of thing. And he was interested in the opposite situation. He was proving some expression has no poles, and he was said somehow, he was for him that appeared in that kind of context. He was interested in some expression being function without a pole. That for him was an important constraint. That's how it was used. Okay. So maybe I'll just quickly walk through what sort of, how do you set up the enumerative problem in that corner? So just, and let's just do it in an example. So we already decided that for Grassmannian we need maybe like half of the. It doesn't matter. Maybe we'll draw this half. So this is K, and then this is about Grassmannian Kn. And so this is the ordinary problem. So if we wanna, what is this supposed to be? This is supposed to be this object here. This is, so previously it was a vector space of dimension n. Now this becomes promoted to this guy becomes bundle of rank n on my curve C, and then there's this sub bundle. Okay. Where I think of this bundle as being fixed, and this bundle is allowed to vary. Right? And so now, if my curve is spec C, then what does it mean? What does it mean to be a bundle of rank? So it's now CZ, and this is, what is it supposed to be? This is just this means projective module over Z of rank n, but that's just okay. That's just just Z to the n. There's not so many options there, and then it just means a sublattice. So if it's a subbundle, it means a sublattice. And now this inclusion. So this is when we're doing the difference between maps. So we've been going through various notion of maps, quasi-maps, and so forth. So if I want an actual map, this map has to be an actual subbundle. So if this is an actual it's a bundle, this means the quotient has to be torsion free. But I can allow the quotient if instead I want to talk about quasi-maps, then I can in principle allow this quotient to be a torsion module. That makes sense. So not Z. Let's forget Z for a second. On a curve.
Are you saying a philosophical statement, or are you saying a literal statement? Big quasi-maps take Z point, the points of respect to the individual.
Right. But even before that, I'm just reminding you what's the difference between maps to the Grassmannian and quasi-maps to the Grassmannian. The difference between maps and quasi-maps to the Grassmannian is that this could be this is for the actual map to the Grassmannian, there has to be a subbundle. And so for a quasi-map to Grassmannian, it could be a subshift that the quotient has some torsion. And so similarly here, this map is either what does it mean that the quotient will have some torsion? This means this is sublattice, this is saturated sublattice. If actual map, and any sublattice if quasi. Rank K, right? So this is a map of lattices. This is injective, but need not be. You can like suppose if you take a lattice, you take twice the lattice, then this would be a quasi-map. this will have, so quasi-maps will have to have some singularity, and that will have a singularity at the prime 2. And now we need some sort of, previously we had a notion, so in this situation when C was a curve over a field, we had a notion for degree of this object, right? So the degree of this map is roughly the degree of this bundle. So now we don't really have this notion of degree yet, and this is because our curve, this is this is not complete in any sense. We need to add, the Archimedean point. So we take z plus the Archimedean infinity, and what you yeah. Spec Z, yeah. Spec Z, yeah. C spec of Z. And in general, something called Arkelov theory, it says what you're supposed to add to arithmetic scheme. What you're supposed to add to arithmetic scheme at an Archimedean point, and what you need to do is you need to add some data of a metric. And that this metric here is just really metric on here. So this is now we just rigidly look just z n plus metric. What? Metric on here is metric on this module. So this is just really bilinear, positive definite bilinear form, which is the same. This is the space of this is the space of. The same as lattices in Rn up to orthogonal. Yeah. So this is phi1. And now here I have some lattice. Draw something which looks like a lattice. Let's say n equals 2. And now I'm thinking about either, if I want to saturate the sublattice, maybe this would be maybe k equals 1. So I take a one-dimensional sublattice. And now the analog of degree, that's just, the analog of to the degree, you should think of this as maybe exponential so the way maybe I'll can't explain really everything. Maybe I'll and it's also kind of from Lie theoretic terms, that from Lie theoretic point of view, this is also natural. This is you take well, what's the size now? The size, maybe you normal, you can, so this is the ambient thing we fix. So we can, this is, this has some, there's some fixed lattice. We fix 1. And now we're looking for sublattices. The size, the natural notion of the size of sublattice, it's just you take the volume of the quotient, or volume of fundamental domain. Just write the volume. For the volume of fundamental domain, you would like to write the volume or a covolume? Volume of sublattice. And you put it traditionally to the power of minus s. So where s is kind of like the logarithm of s. And you can do this. This is the problem. So while this sort of expression, so you can have summation over sections. The general thing you write is some kind of height of the section. Sections maybe called f, height of the section f to the power minus. Height is something you define analogous. This is analogous to that. It's not known to me how have any kind of cohomological interpretation of this function, but it's completely analogous to what we had before. And maybe the more the more what should be true is that this expression, so maybe I'll erase this part. So to continue with this board, so what do we have here? Here we have here we have a module. So maybe forgetting this guy for a second. Here we have a module over a certain algebra, and we're tracing, taking the maybe. So this is algebra of correspondences. This thing is graded by degree. Correspondence, and then we have a module. We're computing the graded dimension of this module, and this you can then this you can continue as saying, well, this is going to be now the Euler characteristic of some so this is let me say this. So there's an operation here, some algebra correspondences. In this algebra, I have a certain commutative algebra. Moreover, I have a certain Clifford algebra. Over a certain commutative algebra. So then I can maybe write it Cliff. We'll talk in 1 minute about how this comes about. And so then you can write, well, this is the Euler characteristics on kind of like the so if I write a spec of Clifford algebra, is that acceptable notation? It means a supermanifold, where this is underlying, this is your underlying actual manifold, and there's a super direction. So if I have an algebra, and if I have some space with bilinear form, linear over that subalgebra, then I can have a. So in other words, this has some generator such that their supercommutator lies in here with some bilinear form. So, and so then, this over this kind of the spec of this cliff. Over whatever this module corresponds to. So this is a sheaf corresponding to great. And then somehow S, this is everything equivalent under GL1 or whatever GL, some copies of. Z is some variable that defines a grading, so under the action of Z. So this equivalent Euler characteristic is just, that's my trace, right? Didn't say anything. And while I don't have cohomology, so this is maybe cohomology, this part here. Well, maybe I don't know what I should put there, that I don't know. Maybe some people know, I don't. But I don't know, Flach. You know, there are people who talk about like Arakel of cohomology, so I don't know, just I don't know. I was hoping to talk to Matthias on this trip, but it didn't work out, unfortunately. So hope everything is well. So this is, I mean, anyhow. So while I don't know what to put it here, this expression, I mean, I'm not sure. You know, in some examples that's an actual equality, and in many other examples you can certainly reasonably conjecture it. Somehow, there's no ingredient here that required any kind of cohomology. You can just say something, and that sheaf is in fact, that sheaf is some kind of twist of the spinor bundle.
Statement about what the sheaf is not a tautology.
No, it's not a tautology at all. Yeah.
It was tautology until you wrote that.
Yeah, exactly. Yeah, it was tautology, but this is some Clifford algebra. It comes with a an example. Comes with a spinor bundle, and this object is one that's inequality. And that is, since we have L-genera in the title, you can kind of call this. This is one of the definitions. This is one of the definitions of this L-genus. Some kind of L-genus of. Yeah, not exactly. I mean, it has something to do with L-genus. I didn't get to that point. I mean, it's still far, so we didn't get there. So, right. So, but at least you can. Yeah. Why? Right, but this is going to be what? This is going to be, so maybe I'll explain 1 second. So then this is going to be, I don't know, it might be slightly disappointing, but
Where are you going? Where was W on that?
what?
Where's W? He's making a statement without W. Okay, so there's no W.
I think here I'm dealing with half of this. Remember already, this is the analog of that. I told you you take like a half. You take a half.
If you know what is the, you want to put W back in.
Excellent question. Yeah, or put some sort of, you know, what to put. Right. So this is, where is this? So what is this? Where is the Clifford algebra, and what is, you know, what's this business? So okay. So then again, back in the familiar situation, we have correspondence. So we have this correspondence as D. A comes from what? So I have my curve, C. So now maybe let's see be an actual curve. C cross, you know, quasi maps. So what does it mean I can add? What does it mean I can add and remove? So what kind of correspondence I consider? I consider correspondences is my you know, they add and remove singularities to quasi-map. So a quasi-map is what? Quasi-map is, first of all, so quasi-map is, first of all, it's a map to the stack. So you can, so this is what's a map to the stack? It's a principal G bundle where G is your gauge group plus a section of the associated bundle of prequotients. Stability doesn't matter for this discussion. And now how do we can modify? We can modify the bundle by some kind of Heike modification, and then we can study what can we do with sections so that to preserve whatever we had before. And that's this BFN construction. And anyhow, this happens at the point of the curve. We take something, we modify. So we have some kind of correspondence between the same thing in here, which changes, strictly changes the degree, and so anyhow. And so now to get a map from cohomology of this to cohomology of that, we have to take Kunis components of this correspondence. That makes sense? And so when you take the Kunis component, that means what? That means you have some operator associated to points, some operator associated to element to one cycle, and some operator associated to fundamental cycle. So you have some sort of some kind of operators. I don't know, EI associated to class gamma, where maybe EI gamma is elements in A. Where
Are you saying that this kind of ACK operator, so the ACK operator is not well defined, you usually put like stable buttons rather than matrix. Are you saying that it does make sense if you put like stable fuzzy maps?
So because it modifies at a point, whereas the stability is imposed at generic point. So if you modify any one you want, any way you like, you're not going to change the stability. Yeah. So and they satisfy from kind of clear that if I take the commutator, so if I do modification at two different points, it's quite clear they don't they commute. Right? So in other words, you get relations of the kind that you get if I take something, a commutator of two things that related at two different points. This is something. It doesn't matter what it is, but had to do with now the cup product of these two guys. Cohomology classes. That makes sense? It means it's like the usual, like if you've seen Nakajima operators, that's how they commute, right? And so then this tells that what? That if anything point anything, they all commute. Right? Because point cup point, that's just 0. And then so this is the commutative part here. And then anything kind of one cycle, they well, maybe there should be a supercommutator. So this is a supercommutator. This is formal Clifford algebra. Over this thing. That makes sense? Right. And so so this is a commutative algebra. And so what this guys generate, so this algebra is commutative. And the spec of this algebra, so maybe I'll write it for, maybe I'll write it A2, and this is A1. For the spec of A2, you can study what it is. And what would be this is some kind of X check 0. It means the singular guy. And so sorry. In specific example, you can verify that this is true, and this is then I'll say a few words in terms of when do you expect this thing to be more general than this. And then moreover, so this is.
So is the subscript EI the island?
It's just some operator. It could be more than one correspondence. So there's a whole bunch of correspondences which you can, but whatever they do, if you take it, if you take their Kunis components, the homology label, they're going to multiply. No. This is just this is with whatever coefficients. This has nothing to do with. This has nothing to do with. So this is independent of the curve. This was cohomology with some coefficient that will be x check 0 over that. X check 0 was defined originally over the integers. And then this would be this x check 0 over whatever coefficients you take. Over coefficients.
On this side, you have a curve.
Yeah. But this the h2 of a curve is. But h2 over so h2 so Vivek has a little bit of a point, is that this h2 of a curve is essentially independent of the curve, except if we think about Frobenius, this will have an action. So Frobenius will scale this. So this is in general, this is x naught check, it's some kind of cone, and makes sense that this is scaled. And this will be really scaled by Frobenius. Because Frobenius really scales h2 of a curve. And then yes. Yes, this is the BFN. That's right. So maybe this is BFN.
And what do you mean that, like with the explanation one that we will explain later? It's not always.
So this is right. This is something. So this is this. I don't know. I mean, I'm just the talk. I'm just kind of getting to the subject of the talk after 2 hours of wandering around. So anyhow, so this is. So now, now what's it going to be? So this is then I take. Then what is. Then what is. Then what is a, so to speak, kind of EI gamma? What these things, where do these things lie? So these are, so if you think about the, okay, so maybe I'll skip a few statements, a few things, but this is some operators that, first of all, this is this guy's for some kind of, I mean, they form a Clifford algebra over this. So in other words, this is supposed to be some kind of sheaf of Clifford algebras over this guy. And what it is, it's supposed to be like, this is, maybe I'll write it like that. So first I write it's a Kähler differential of some sheaf over that, and then I have the tensor with H1 of my curve. But better write it like this. Better write it as H1 of the curve with coefficients in Kähler differentials. What? A gamma is an H1. I didn't say anything. Let's just say my fixed vector space, and I want to tensor it with cohomology. I might as well take cohomology with coefficient. This is fixed vector space.
Over here, E1 gamma was on this side.
Right, but they're now supposed to. This is now supposed to be sheaf over that, right? This is a. So if I take a Clifford algebra over some commutative algebra, then this, if I sheafify this, I'm get a sheaf of Clifford algebra. So sorry, Cliff. Yeah, somehow in. Yeah. So this is in here, and then they generate maybe in the cliff of that. And the reason this is, and the reason I get this is set with quadratic space, and the way quadratic space is because this has symplectic form, and this has a symplectic form. They together form. Right. So this is with the symplectic form here, symplectic form there. Give me a form. Okay. And so now I took a coefficients. Here I took coefficients with some trivial. So I took coefficients in C with trivial local system Kähler differential. I might as well have a non-trivial local system. I can have these correspondences. So now maybe I'm coming. So this, so then this is may very well be non-trivial local system. Let's see. And how we should enrich BFN construction? Well, in principle, we can take could put non-trivial local system here. And that would be, so what would that mean concretely? So for instance, let's go to the very first example. If I want to somehow count points in the symmetric products of a curve, right? So instead of counting points in symmetric product, I can count points together with trying to remember what this D tuple of points adds up in the Picard of my curve. That is to say, I can, right, somehow, I don't know if it's a meaningful setup in physical problem, but in general, if you have some kind of, in the original question, you have some kind of, you count maps from a curve somewhere, like, I don't know, quintic threefold. Then in principle, you have a line bundle in the target. You can ask, what's the pullback of that line bundle is your curve in peak of your curve? How is that distributed? Similarly, so if I'm going to, on my P naught, although it's P naught is not, there's not so much in P naught, but on P naught there's a line bundle of 1. I pull this back and just saying, where do my points in the curve, where do they add in the Picard variety? And that is to say, my quasi-maps would be in this sense, would be living on the Picard, over the peak of my curve. And I can in principle pull back some non-trivial local system from the peak, some character, and count with the character. This would be saying, I'm going to do the Dirichlet function. And so now for my correspondence to be equivariant, well, I will need to put, if I had some non-trivial local system on peak, when I add and remove points, well, I have to use that local system on C. So that means, so this in principle, this guy here in principle may very well be a non-trivial object. And more generally, so this is where I come to the fact where it's in general there should be a generalization. Maybe this is kind of interesting point of view of this. Maybe in some sense, since I imagine most of you thinking more in terms of, what is it, whether this says anything interesting about physics as opposed to saying nothing interesting about nothing. So there's the in general you can imagine that this is, instead of non-trivial local system, you can in principle replace it. This you can further replace by pullback. So quasi-maps from the curve to anywhere, they always, so if I take quasi-maps from my curve C to any quotient, whatever y mod g. This always, so by definition, what's a quasi-map to quotient? It's first it's a principal G bundle, and then some section. So it always sits over bun G. Or quasi or maps to the point mod G, right? So this always is. So pull back a Hecke eigenschiff. From bun G. And then you'll have, and then your, then you'll get, then you'll get some bigger algebra, because when you do Hecke modification, it's you have a you have this sort of non-trivial local system entering as your eigenvalue. So your operator will also have degrees of freedom in that local system, and so this would be something genuinely bigger. So in that situation, this would be genuinely bigger than BFN, I think. And so in particular, if I take, like for instance, if I take Grassmannian Kn, well, in principle, I can imagine that I can, in principle, write it as a product of the quotient of GLN mod parabolic. And so in principle, I should be able to pull back have a function of a k bundle and n minus k bundle. This corresponds to the fact that they are here when I sum over these lattices. I don't have to put just the volume. I can put any function I want of the actual sublattice and any function I want of the quotient lattice. So this is, in principle, I can write stuff like this. And in this case, spec, if I just look at Langlois' formula, I mean, yeah, I should also say that a lot of what I'm saying is, well, there has three ingredients. One is pure speculation. Second, few examples I understand. And third, there are classical formulas in number theory due to Langlois and many other people. And so so if I look at just the Langlois formulas, then I think in this instance, this should be the blowdown of T star, the dual Grassmannian. So not the BFN. With BFN would be some slicing here. So in other words, maybe to summarize this, oh no, I'm going like closing on 2 hours. Oh, hey. Oh, what a surprise! Yeah. Yeah. Anyhow, so this is what I think. There's some variety which is not the BFN dual, not the S dual, but something which is more like that. And it's just, and what is it? It's just, you think that this is some degeneration of just the orbit of GLN, right? So this is GLN. Deformation of that would be just an orbit of GLN, and you would imagine that in general, if you're any kind of variety X of you after some deformation, it becomes homogeneous, and so you just take if there was some Langlands duality for this infinite dimensional groups of automorphisms of deformations of your X, that would be just the orbit of the Langlands dual, the corresponding orbit of the Langlands dual group. Anyhow.
I don't quite understand. So,
Yeah.
I mean, I believe that you can construct more observable,
Yeah.
If I consider the also line. Why would somehow you say it's natural the fact that it's all in a bigger space, that the line observable is not like really different kind of observable, it's a different kind of question? you say that I have more time at home and become more observable? I guess you can. Maybe someone for your application, it's natural to consider all possible observable, line observable, surface.
I don't think they have to do with lines. It's more of a question that if I take I mean, that's exactly the kind of, so this is a natural generalization of the following kind of example of the following kind. Like suppose I study any kind of, any kind of problem about mapping your curve someplace, any kind of target. And if there is a line bundle or vector bundle in the target, I can ask how is the pullback of that distributed over my space of maps. It makes sense, right? And I don't think we study that sort of questions in enumerative geometry, but it's not unnatural to ask this sort of question. And the way to address this question is probably by some kind of harmonic analysis, namely instead of taking cohomology with coefficients. So how are we going to do it? We're just going to take cohomology with coefficients and some sheaf that pull back from one sheaf. That's supposed to be like kind of a harmonic analysis approach to that question. Like, yeah, I don't know. Well, I don't think it's a ridiculous question. I'm not saying this is the most natural question in the world, but it's not.
But anyway, you say that to make this thing work, you have to enlarge that.
I think then you'll have to. I mean, just if you look at Langlois' formulas, then you will have to. You will need stuff like that. Not the actual BFN mirror here.
Would it have shown up even if you didn't consider the spec of Z?
That doesn't matter. The spec of Z that only shows up in. So the only place where it's going to show up is going to show up in here. The difference between what is my actual curve, the only thing that the curve somehow remembers is this sort of thing. So what's its cohomology in some kind of local system? And so that is. I mean, of course, this is saying, oh, the only thing that this construction remembers about Z is what are the zeros of the Riemann zeta function? Okay, this is. But and so maybe I'll I have to somehow summarize this talk since it's been going on for 2 hours without any progress, or rather maybe regress. Is that you can.
We are flexible.
But
we don't have a firm class, so just section forward.
Yeah, well, I don't know. So this is, maybe we should make a break, let people leave. But maybe we should have done this at the beginning. So maybe I'll just somehow backtrack. So you can imagine you're going to be doing counting problems of this kind, and then what sort of generalization of this counting problem I'm proposing? I'm proposing. People have considered is that you sum over sublattices of a given lattice, and in addition to just multiplying by the most naive invariant, namely the volume, you multiply by any function you want of the sublattice and any function you want of the quotient lattice. And that would be saying that I have a map from my moduli space to bun G for GLK and GLN minus K, and I'm going to pull back anything I want. And then some aspects of this count, I mean not every aspect of the count, but some aspects of this count can be done. Some aspects of this resulting function is captured by what? It's captured by, I can in principle have, so in general. So maybe I'll. try to say. So so there's some we were for curve over a finite field K, actual curve. We want a local system of these things on my curve C. That is to say, I want some action. What do we want? We want some action of the group. An action group of one, or rather get an action. Well, so take pi 1 of C, the geometric fundamental group, goes to gamma, so which is just the actual Galois group. And then this goes to Goldwag group. And then this goes to Z. And this is the order of this Frobenius. So this is, if I have some local system means I have, so previously we had just Frobenius acting on this, and we had the trivial thing, we had just Frobenius acting in cohomology, and this thing was just acting trivially. But now in principle we can have an action of this whole group on, so of the group on this group on A2 or inspect, or maybe X not. Let's check. Rather, that would be and then we can form what? We can take. So what would it mean to even before this? If the fundamental group acts somehow non-trivial in the tangent space, means in principle acts non-trivial in the space itself. So when we take the zeroth cohomology of a group acting on a space, those are the invariants, right? So this is just says, so this says that says the analog, the spec A2. Well, that should be, or at least there's a map. Maybe just equal. You take the fixed locus of this thing, we call this group gamma prime. And then we blow it down. Well, this is in principle, this X check is in principle some algebraic variety, and where this is a fine algebraic variety. And so, but this is, we can always take affinization of algebraic variety, spectrum of global function, and then the Gromper subgroup here. Yeah. And so then this A1, well, this has to do this pulls back. Via, so that maybe call it sigma. So sigma.
This new X check something different from the old one.
That's right. There's in principle some kind of big X check, yeah. Yeah, it's a good point. So what do we do? Make it some kind of bold-face X check. So there's a map. It's finalization. Well, back to what? To the Clifford algebra of now again H1 of this gamma prime with coefficients in. Again?
I'm just confused who it was. So this bold X, that's not X check, that's the original X.
That's that.
Who is bold X?
The bold X check is the new X check.
Bold X check, I understand. What is bold X?
Ah. Thank you. So this is, and then, so if I have a fixed locus, then my group acts in the tangent space, so I can make, the tangent bundle to this X check. Restrict to the fixed locus, right? And as before, this is now, this is, since it's, this was symplectic and this is H1, so this together is orthogonal, so it makes sense to form a Clifford algebra.
In BFN situation, the gamma prime is D. Is there a curve punctured disk or disk?
I don't think they have that at all. I mean, it's just, none of that I think exists, so to speak.
Their construction corresponds to some curves.
But that's just, I think they're.
Which curve?
I think there's a formal disk. But I think that the issue, they get a grading, they get the grading corresponding to the action of Frobenius just because it's like a spec of some cohomology, like a grading on cohomology. It's a little.
So this X check, it depends on the curve?
No, that's the whole point. Is I think that's what I was trying to say. That if I think that X check, that's just something what you should be able to determine from what it corresponds to like for I think there is one for there's one. My thinking is there must be roughly one for every parabolic in my gauge group, and if the parabolic is minimal, that's the old BFN, and if it's the whole, so and the kind of the shifts on Bungie, the automorphic forms, they have some kind of decomposition according to the parabolic, and I think that's the. There's the composition of the space of automorphic forms according to some parabolic subgroup.
Sorry, you think then your X check is going to be a product of BFN space times other stuff?
No, I think in general, I think if I take the biggest boldface X check, then I think the old BFN would be slicing it. Yeah.
How is slice going to be fixed pointed? So for example, in the one example you how would you think that this is complicated proof?
Right.
How is that supposed to act on stereograph one?
Oh, that's easy. So if I have a Hecke eigenfunction here, that gives me a Galois representation that goes into GL. So you have a Galois representation corresponding to.
I'm not asking where it originates.
But this is going to act through there. So there's if I have this kind of automorphic form of this kind comes from from a representation into the dual parabolic group, and that will act on the Grassmannian. So if I have, in other words, if I.
I'm asking really down there.
Yeah.
You think in some example X check is.
So maybe let's say I have some kind of my X is like a you know, some kind of T star G mod P, something like that, right? then I'm asking for some kind of function on kind of band P, right? And that, so if I write a Heike eigenform here, then it will come from representation of this group gamma into the Langlands dual parabolic. And this does act on T star G check, not B check. So right now I'm just thinking this example that just comes from the old business about Galois representation. This acts here. So okay. And so this is you know, what is this space? This space. So this is some space on which you know, this is, so there's going to be some kind of Clifford algebra. This is some space on which here Frobenius and the centralizer of gamma act. That clear? I think it's kind of obvious, right? And then you ask, what would be the character of the, if I take the spinor bundle of this algebra, what would that character look like as a function of Frobenius and, you know, maybe some variables that like the centralizer? You know, if I have a centralizer, that means I can further, you know, split this tangent bundle into irreducibles, in which just say be like a scalar in each reducible. Right? And then this is in each irreducible, that would be just Frobenius multiplied by a scalar. And I'm asking how it acts here. Well, it acts how it's going to act like, how it's going to act in the spinor bundle for this algebra. It's going to act by the L function of the corresponding representation. This is if I have a non-trivial representation of a group like that, then its L function is in fact a polynomial, and it has to do with that's more or less by definition saying how Frobenius then. So this is if I'm interested in the K-theory class of the spinor bundle of this algebra, that, you know, that's some kind of K-theory class that has to do with, you know, some kind of, you know, things we call kind of L-genera. And the way you think, if you have if you have an action of a group like so, then what does it mean you have an action? Sorry, what do you mean you have a topologically study an action of a group like so sorry. Maybe I'll backtrack. Let me backtrack 1 second. So if I have an action of a group, I can on some variety before and I have variety. So also some variety that I can then I can ask you know, what sort of quantities determine the cobordism class of this manifold? Well, I have to, you know, take all possible Chern kind of, you know, take all possible integrals of all possible Chern classes of the tangent bundle, and that will be your answer. Now, if I have a group action, what sort of quantities do I determine the covariant cobordism class of some manifold? Then it's and the integrals of, you know, all possible Chern classes, which then they somehow, you know, the multiplicative ones, they're called the genera, and then, you know, whatever. And okay, so now you have action of a group on some variety and of a group, and now you're saying what sort of quantities determine the covariant cobordism class of this action? Well, what can you do? For every closed subgroup, you can take the fixed locus and take take the churn numbers of that fixed locus, and moreover, that fixed locus, that will be the normal bundle to that. That would be some, not just the normal, also the tangent bundle to that would be some representation of whatever normalizes your subgroup. So this is, you have this sort of, this kind of thing. So in particular, here in this group, you have this very, very special subgroup gamma prime, and you take its fixed locus and take very special kind of churn type expression associated with this fixed locus, and you get some genus. And since it's given by terms of values of L function, it makes sense to call it L genus. Anyhow, but this L genus is the K theory, has to do with the K theory class of the spinor bundle for this Clifford algebra. And what I was trying to say, maybe to conclude this talk, maybe I'll say two things. Is that one is that this, so I apologize, I've been speaking for 2 hours without saying much. This, if I take the spinor bundle over things like that, that would be some sheaf on this algebraic Rho. And if it's actually coherent, like a coherent object, if I'm in this particular situation when this cohomology is finite dimensional, and over Z, this cohomology has to do with, you can define that axiomatically, and then we'll have to do with like the zeros of some L functions and so on. Right. So what I'm trying to say, over a finite field, there's a priori definition of an L function which says that the character of this object is has to do with the L function of representation. Over spec Z, you can have the invert this logic, says you already know what the L function is, and then you infer the character of this representation. That's valid logic. But somehow this would be infinite dimensional representation. It's fine. So this will be some kind of basically coherent object on this algebraic variety, and this object has to do with the counting problems as I tried to explain them. And this I think extends also to spec Z in the sense that for spec Z, or for whatever somehow for number fields, we have some kind of group from genus some number field Q. Now its quotient here would be R, and then some kind of mystical group. But if you have some kind of, this mystical group was introduced by Langlands many years ago, and not much is known about it, but one can use it inverting the logic, like I said here. So you can say, well, the cohomology, you should be able to know what's the character of, if I have some purported representation of this group, then at least I should be able to say what's the fixed locus. Well, that fixed locus only will depend on anyhow. Fixed locus of any action also depends on some data like Zariski closure of a group, so it depends on very few things. So you have an action of an object like this, you can define these things in a way I explained, and then they will have to do with the enumeration of things, with the enumeration with analogous kind of point counts for over spec or number field. Now it's been, oh no, sorry guys. I mean, I really appreciate your being so extremely patient with me being lost in this woods. Yeah. Yeah. Right. No. Even before this whole thing acts, right? So it's not just reviews act. It's this whole thing in principle act. We started with an example, but this action with this trivial local system is a trivial group. But in principle, if it's a non-trivial coefficients, then you'd imagine this whole group acts on on this guy here.
You said that how do you get an X check? Big X check?
So
How do you define a big X check or big X check?
well, I don't know how this is. What's the BFN? Maybe it's not so complicated. I think this maybe.
You said only the gamma of primary variances at the end of the thing.
Right, but I think it's, you know, my thinking is it's maybe not so complicated to define this thing. This could be something. It just eludes me what it is, this definition. But I think it may be easier to define this object than to define the actual BFN mirror. I think this may be a kind of better object. Yeah, sorry. Maybe I have. At least you witnessed the state of my confusion, and so that's.
I stopped understanding anything when you started talking about this coefficient. What was that? Explain again what this coefficient.
So this is when we. Oh, here. So here's an example where we're trying to count points in the Grassmannian, right? And so the way we set it up, we're counting sublattices in a given lattice according to their volume. But this sublattice in a given lattice, that is. By some function, yeah.
How does that translate to this?
What it translates to what? It just means this means I have from the maps here.
What is it? Maybe you can write it in the thing it's sitting over.
Yeah. So if I have, suppose I study maps or quasi-maps, doesn't matter. So maybe let's say quasi-maps from my curve C to whatever mod, Y, mod, and since this is not reductive, let's just write P. And this really maps the quasi-maps to C to point mod P, right? And that is, and this is in this instance, I can. This really is the data of the lattice and the sublattice. Right? I mean, also the extension class, but so maybe we'll mob those who quasi-maps to point model kind of levy of that P. That is really lattice and sublattice. So if I want something like if I were doing this on over a finite field, well, what would I do? There would be some kind of cohomology group, and the way to incorporate this data is to pull back some sheaf from ban M to my space.
What kind of sheaf?
Some Hecke sheaf.
No, I just meant like this.
Yeah.
Constructive sheaf.
That's right. Yeah. That's right. Yeah.
Okay, so you do that and then what?
And then so if it's a Hecke eigensheaf, that means what? That if I make a Hecke modification, the thing doesn't go to itself; it goes to itself, tensor some local system. And so that means my correspondences, in addition to being all the indices they had before, they now have further indices, which says in whatever each one of them, each one of those correspondences is some kind of Hecke modification.
They have C times this quasi-mass times on the Langland's dual side to
Some bunch of representations, yeah. And so now all these guys now carry indices in this representation. I mean, somehow to tensor multiply this representation. And so in principle, I get something, which a priori looks bigger, I think will be bigger.
So you do a black hole that has that stack of that.
Yeah, exactly, yeah.
And then you conjecture that in this case it's bigger.
In this case, it's just the dual Grassmannian. Yeah, that's a reasonable conjecture, I think. But I think in general, this must be an object which is somehow easier. It's somehow an object which is.
And is it tautology from the other thing you said that if you take this bigger thing, take it static, and take this fixed point, et cetera, stuff, and get back to the other end?
No, I don't think it's that. It's I'm a little, you know, not 100% certain how what's the relation to BFN should be exact, but I think.
You know which thing was BFN? It was BFN when you like killed that extra factor.
Right, but that's, you know, here you have.
So I'm confused about something else. This new thing you described.
Mm-hmm. It still has this. So whatever it is, it's still the points still commute, and this guy still.
Why is it any?
Because this guy also now carries, you know, a lot more indices to it. I mean, a lot more labels. Yeah. Yeah. It is a Tomer representation. Yeah. So. Right. So there's some shift here which I want to pull back here, and then to make this correspondence to be Galois covariant, I will have to add more. I will have to introduce more operators, which the operators also have some kind of indices in the representation. Right.
Is that correct?
Well, I mean, in principle, there are many modifications here, each of which has its own, you know, its own local system as an eigenvalue. But in principle, yeah. Right. In principle, they go to somehow. Right. I mean, right. Spec G check, something like that.
It's really true. One C that's quasi-maps not close to G check.
No, I'm not sure. So I thought I was more thinking about specific situation where I have specific Hake eigenshift and I get some specific local system eigenvalue, somehow local system eigenvalue. But I'm not sure what you know. I'm having like finely. I mean, somehow in my construction involves like, you know, finely many local systems, just specific. Because I have finely many correspondences, each of which is somehow, yeah, maybe not finely many, but I know countably many correspondences, if you want. I mean, if I have some kind of, if I act by correspondence, some Hake eigenshift, I get, you know, like an extra local system on C, right? But some kind of fixed local system. I don't need them all. Right? Since I'm acting by some fixed operator and some fixed eigenshift, I get some fixed thing.
I thought you wanted to consider all the Hake eigenshifts. And before you wrote, because there was conflict.
Maybe one can cook it like that too. I'm not sure. So maybe. Yeah, right now I'm thinking I pick one Hake eigenshift here. I think what's important is only what I think is important is only the. It's only like the